All right, so picking up where we left off, summation notation. So far we've defined a sequence as a mathematical pattern. And it could involve factorials, it could involve exponents, it could involve multiplication or addition. A mathematical pattern, subtraction, division, all sorts of things. Well, now we want to say, well, what if we have this pattern and we want to sum all of the numbers in the pattern up? We use this piece called summation notation. And the idea of summation notation is this piece. This is our definition. I want you to add up a specific amount of numbers in a pattern. The first 5 numbers in a pattern. The first 10 numbers in a pattern. That's what this will answer. And what it means is you have to know what each one of these letters stands for. So AI, just like we've seen AN in the past, that's the pattern. That's the definition of the pattern that we've seen in the past. All right? That's not changing. We've kind of already seen that today. The 2 numbers that are important are I and N. I is called the index of summation, and that's where you're going to get the first number in your pattern. All right? I is going to get you the first number in your pattern. And instead of saying pattern, I'll say sequence. The first number in your pattern. N is going to be the last number in your pattern, or in your sequence. And then obviously, you'll be responsible for getting all the numbers in the middle, and you can use the formula to get that. The first number, and then you're going to add up all the numbers, and you stop at the last number in the sequence, the upper limit of this, N being called the upper limit of summation. And let's see. This Greek letter, when you draw it like this, all right, that's sigma. All right, it's a Greek letter. It's essentially saying, sum up all of the terms between I and N. All right, 1 is the lower limit, N is the upper limit. Again, those can change. A lot of times you'll see numbers in place. Here's an example. So here's a summation notation of I want the terms 1 through 5 all added together. So what are my first 5 terms? And I look, well, my first term is 3 times 1. 3 times 1, so that's going to be 3. So I'm going to have 3 plus, now I need to get my second term, 3 times 2, it's going to be 6, plus my third term, 9, plus my fourth term, 12, plus my last term, 15. And I know you're probably tempted to put all of this into a calculator, but I will show you a little trick. Sometime with summations, the first and last term adds to 18. The second and second to last term also add to 18. That's essentially 18 times 2. Obviously, middle term is going to be 9, so 18 times 2 is 36, plus 9, 45. That would be the summation for the first one. Here, I'm asking for the third, fourth, fifth, and sixth terms added together. So I'm going to need to start with the third term, 1 plus 3 squared. That's going to get me the term 10. My fourth term in the sequence, 1 plus 4 squared, is going to be 17. 1 plus 5 squared is going to be 26, plus 26. And my last term is going to be 37. This one I can't use the same trick like in the last one, so I'll just have to add it up. Let's see, that's 37, 47, 57, 63, 73, 83, 90, I believe. One last summation here, just for a little extra practice. I'm adding up the first 8 terms here, but notice my first term, as those actually be 9 terms, they start at 0. 1 over 0 factorial, we talked about this in the other video. That is going to be 1. All right, that's our first term. 1 over 1 factorial is going to be also 1. 1 over 2 factorial is 1 over 2. 1 over 3 factorial is 1 over 6 plus 1 over 24 plus 1 over 120 plus, and that's 5 factorial, so now I have 6 factorial, 1 over 720 plus 1 over, now it's going to be 7 factorial, 5040. And then 8 factorial is going to be 1 over 40,320. All right. essentially, the easiest thing to do at this point, while you could get common denominators, if you really so desire, a calculator will give you a pretty good estimate. 2.71828 would be a estimate if you just type this into a calculator. Our summations do have a couple of properties that are nice, and if you need more of an explanation, I'm happy to go over them in class. The summation of C, where this C is a constant, and again, a constant is just a number. If you have a summation of a constant, well, that means every single term is that constant. So the easy calculation is just C times the number of terms from 1 to n. That's going to be n is going to be the number of terms. If, say, you maybe don't have, if you don't have just a constant, but you have a constant times your sequence. So this is your sequence. Right? If you have a constant times your sequence, you could take that constant and actually put it on the outside and do it at the end of the problem, because it's essentially a distributive property or a factoring. And here, the summation of a sum is really just the summation of the individual sums. The sum of the summations, I guess. A summation of a sum, that's what this first part is saying, a summation of a sum is the same as the sum of the summations. So this is a summation, and this is a summation, and you're summing them together, adding them together. So those are two equivalent ways to simplify if it helps you moving forward. All right, series. A series is essentially what we've been working on. Consider the sequence. So they give you this sequence A1, go all the way up to AI. There are two types of series. There is a finite series and an infinite series. And essentially, a series is the sum of the first n terms. So if you've got a countable amount of terms, then you're going to say it's a finite series. Another word for finite series would be partial sum of a sequence. So a sequence is really a pattern, where a series is really a summation. And then the sum of an infinite sequence, where the difference here is you are going all the way up to infinity, that's called an infinite series. So the two big words here, finite series and infinite series, and it just really means whether you're doing, it's essentially a summation, and you are calculating either it's a finite amount of entries or an infinite amount of entries. It's exactly what we did on the last few pages. We have been working with them, calling them summations and series. They're pretty much interchangeable. All right, so here we'll do one real quick problem and it'll be finished. We are going to find the third partial sum. So I know I put infinity here, so there's two parts to this. I'm trying to kind of do two problems at once here. This we are really using for here. To find the third partial sum of this, that's going to be from I equals 1 to n equals 3 of 3 over 10 to the I. So I'm really looking for three terms. The third partial sum means three terms. Partial sum is another word for finite series. All right, it could be the same exact piece. So the first term here is going to be 3/10. Plus, second term would be 3 over 100, and the next term would be 3 over 1,000. And if you were to add that up, it would be 0.333. That would be the finite sum of the third partial sum. All right, now the difference here, if I take this statement and bring it down here, now I want the infinite sum. So I want you to keep going and never stop until you reach infinity. Well, if you notice, your first term, we called it 3/10 before, right? Your second term, we called it 3/100. Now, whether you use fractions or decimals, your third term, we already did this part, 3/1000. Your fourth term is going to be 3/10,000. And your fifth term is going to be 300,000. And I'm hoping you're seeing a pattern that I don't need to keep going. I bet you could guess my 6th, 7th, and 8th term. Because essentially, if I tried to add these up, what I'm doing every time is I'm adding a 3 to each one. I'm adding a 3 onto the end. This 3 is going to go on forever, So if you're seeing that this goes on forever, you realize that that is the fraction 1/3. So that would be the sum of the infinite series.